So far we have been still picturing very regular shapes of things and problems, but in many practical situations you have shapes that cannot be exactly sticked to a rectangular grid nor to any other grid that is equidistant. So the problem is that then you have in fact to construct the boundary out of rectangular steps. Well, this is something that works, but has another error which is much bigger than, for example, the discretization error itself. So this is the first approach you could do, is not to investigate in fact a circular shape, but a shape that is constructed by rectangular approximation, something like this. Well, for some classes of tasks, this could have so big error that it's not very useful. For example, if you have a horn antenna which is constructed of a waveguide and then, for example, has this shape to get good matching between the wave in the waveguide and the wave outside where the impedance is lower, then changing this into a set of steps makes a big difference to the geometry of the problem, and unless you use a very fine discretization, the results you obtain are not very comfortably similar to the results of the real problem. So then there is something which uses special elements of the grid that are mostly derived using integral form of Maxwell equations, and that, for example, are derived for a semicircular wall or other shapes. So if you have, for example, an experience with a program like Microwave Studio or Quad or other programs that use finite difference time domain, they mostly use a lot of special boundary elements that are prepared to do the boundary jobs, but are not derived based on Maxwell equations in differential form. They are derived out of Maxwell equations in integral form. That's something that shows you the quality of a software if you decide to buy one. The important point is not the implementation of the algorithm inside the media, but the boundary problems and the mesh generation. I would like to make another comment which in fact used to be very important a few years ago, and that is an attempt to get rid of current condition. As I have shown you, if you need to get calculation of this example at higher frequencies, you would have to decrease the space step, but also the time step. So in fact, increasing the frequency one order up requires you to decrease all three space steps 10 times and the time step 10 times, which prolongs the calculation 10,000 times. That's something that is beatable but needs a lot of resources in computation. So there have been attempts to arrange the time solution in a different manner. not to use the leapfrog algorithm, which is simple. At the beginning we told we know half time step future values, and based on them we can easily make a recalculation to time delta t. Then we elaborate the other values, 1/2 delta t ahead in time, and based on this the leapfrog algorithm is capable of solving the whole set of values, both discretized in delta t, 2 delta t, 3 delta t, or half delta t, 3/2 of delta t, 5/2 of delta t, and for each of the values you just have one simple equation. You can also arrange the equations so that you in each brick with 6 discretized values ex, ey, ez, hx, hy, and hz have a set of equations within which any value depends on the others, and by solving this set of equations 6 by 6 matrix, you can get the future time value of all 6 variables without the stability constraint. So in fact, in theory, you could have an arbitrary large time step. Those methods have been quite discussed, quite published somewhere around the year 2000, and this was very promising because by increasing the time step 100 times you could really decrease computation time. But then there was a very interesting paper which compared calculation of the same problems using leapfrog algorithm, the old one, and the new one which with increased time step. And it has been shown that although the algorithm is stable, the numerical error increases so much that you obtain the same accuracy faster with the leapfrog algorithm. So since then, the number of papers on the new methods rephrasing FDTD equations without the current condition burden have decreased, and I am not aware of any paper within last year. So that's an important point. There have been other formulations of finite difference time domain method, and at the time being they are not very trusted. Now this is all I wanted to tell you at the beginning of FDTD. I'm sure that you will during seminars have some tasks and some snippets of code in MATLAB that could help you to watch what really happens during calculation. I would like now to switch to the second topic I promised last week, and that is the transmission line matrix method, TLM, based on Huygens principle. In fact, this is the predecessor of finite difference time domain method, an earlier method, and I would like to show you the basic principles of that. Just first the Huygens principle. In the Huygens principle, which is several centuries old knowledge, you have a point that has started to oscillate, or the wave has arrived to the point, and the point is oscillating with some frequency and magnitude. And the Huygens principle says any point to which the wave has arrived becomes a source of a wave. So in fact, you can get the wave propagating out of this point. And if you have a plane wave, then it arrives to a set of those points at the same time, and those points that are just visited by the wave become new sources, and if you add the waves radiated by those sources, you get another plane of the plane wave at which you have again a set of sources. So you can consider any point that has been reached by the wave as a new source of the wave radiating to all directions. Now this principle has been incorporated into a computer, and surprisingly the implementation is very easy. If you have a square grid, again I show you only a 2D example, the 3D is straightforward then. So if you have a plane grid, due to Huygens principle, if you have, for example, here a source of the wave, then it becomes radiating to all directions. But within this grid, you approximate it so that it only invokes some descendant waves in the four neighbors. So here, 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 and here. Let's say that we talk about voltage or electric strength. So if we have the magnitude of 1 here, and we arrange the grid so that the propagation time and the time step are set so that propagating 1 delta x or 1 delta y, that is one connection in the grid, propagating to the second point, takes just one time step. In fact, any source here in the next time step is converted into 4 sources in the neighborhood points. So in the first step you have then in the second step you have those 4 sources, and now all of them become again the sources of a circular wave, so that in the next step, I hope I have some black pen, you would also have fed those points and it runs for any next time step so that any point feeds his 4 neighbors by a wave. How much magnitude could you invoke in your neighbor points so that the energy conservation principle is not violated? Well, it's important that the energy is dependent on the square of field strength or voltage. So if we have a 2D case, then energy conservation principle tells you that out of 1 over here, you would, in the next step, experience 0.5, 0.5, 0.5, and 0.5 magnitude of the voltage wave in the neighboring points. So then, in fact, you can do this in reverse order and say, okay, so for this point I have just here, the next time value would be a sum of 1/2 of the value of the neighbor up and 1/time of the value of the neighbor on the right side and 1/2 of the value of the neighbor down and 1/2 of the value of the neighbor on the left side. If this is the true, you can update any point using the values in its neighborhood. So we have a valid algorithm to get a time step in the grid. For any point, we would repeat that the value in the time plus delta t, and let's make the same indices like we had in FDTD derivation. So this was 1, 2, 3, and 4. So the value is given by V1 plus V2 plus V3 plus V4 divided by 2, and all of those values are at the time. I will make it as a down index because upper index would seem like raising to a teeth power. So this is what you do for any of those steps, and you just sweep through the grid, updating the points with the values of the neighbors divided by 2. Now, of course, to sweep through the net, you have to first update this value, and still you have to remember this one, so that you cannot just do it like in FDTD that you forget the old value. You have to keep this value for the update of the next point here. So it's a little bit more complicated as to programming, but it runs very fast. Now, the important point we have based our calculations on is that it takes just one time step for the signal to propagate one connection between those two nodes. And this is a crucial point because it can handle, and that is discretized, free space quite easily. But what if we have some boundaries at the ends, or we have the area of interest filled by different dielectrics? That's the next question we will handle just now. So first, what if we have a boundary which is, for example, metallic? The end of the net is an electric wall which shorts any voltage. So if we want to handle this, the easiest way how to arrange this is to make a special cell so that you have the discretization grid, and the metallic wall now is only half space step distant. And what the trick is, let us see the wave that propagates through the structure. It is in this point. So if the metallic wall is just half space step, the wave from here to here would only cost 1/2 of the time step. And if it reflects back, it gets here just after 1 time step. So in time with the responses reaching from other points. So in this case, we can update this point. Now I will again use this. This is the updated point. According to our number scheme, this is 1. Point 2 is missing. Point 3 and point 4. And instead of receiving the input from the missing point 2, we received this value reflected back from an electric wall that is reflected antiphase. So in this case, we will have the update formula, voltage in the next time step, and it would be V1 plus V3 plus V4. Those 3 values we will really have here. And instead of this, we would get the same amount reflected antiphase. So we would have minus V0 and that's it. So we have now created an update formula that can update a point which is half space step distant from an electric wall, from a perfect conductor. For a magnetic wall, it's as simple, just the reflection would be in phase, so we would get here plus V0.